Good morning students, let us continue process synchronization. In the previous video we have studied about critical section, mutual exclusion, etc., semaphores, so on. Now classical problems of synchronization. In this section we present a number of synchronization problems as example of a large class of concurrency control systems. These problems are used for testing nearly every newly proposed synchronization scheme. In our solutions to the problems, we use semaphores for synchronization since that is the traditional way to present such a solution. However, actual implementations of this solution could use mutex locks in the place of binary semaphores. Here, there are three problems: bounded buffer problem, readers and writers problem, and dining philosopher problems. And one more thing, as we discussed about bounded buffer problem and readers writers problem in the first module, I will skip those two topics now. You can study the textbook or notes or PPT for those two topics. I will directly go for dining philosopher problem, which is the very important classical problem of synchronization. So here you can see a figure, right? A dining table which contains a bowl of rice in the middle. There are 5 chairs, 5 plates and 5 chopsticks. Consider 5 philosophers who spend their lives thinking and eating. The philosophers share a circular table. You see, there is circular table surrounded by 5 chairs, each belonging to one philosopher. In the center of the table, there is a bowl of rice, and the table is laid with 5 single chopsticks. Chopsticks, in the sense, you can call it as spoon or fork. When a philosopher thinks, he or she does not interact with her colleagues. From time to time, a philosopher gets hungry and tries to pick up the 2 chopsticks that are closest to her. The chopsticks that are between her and her left and right neighbors. A philosopher may pick up only one chopstick at a time. Obviously, she cannot pick up a chopstick that is already in the hand of the neighbor. When a hungry philosopher has both her chopsticks at the same time, she eats without releasing the chopsticks. When she is finished eating, she puts down both the chopsticks and starts thinking again. So, just assume that a philosopher can eat only when 2 chopsticks are available. So, in this circular table, if the philosopher require 2 chopsticks at the same time, only 2 philosopher can eat at the same time. Even though all 5 are hungry, only 2 can eat at the same time. The dining philosopher problem is considered a classic synchronization problem neither because of its practical importance nor because computer scientists dislike philosophers, but because it is an example of a large class of concurrency control problems. It is a simple representation of the need to allocate several resources among several processes in a deadlock free and starvation free manner. So, in this particular situation, the chopsticks are equivalent to resources and philosophers are equivalent to processes. As we all know, a process needs required to execute. Here, a philosopher requires chopstick to eat. One simple solution is to represent each chopstick with a semaphore. A philosopher tries to grab a chopstick by executing weight operation on that semaphore. She releases her chopstick by executing signal operation on the appropriate semaphores. Thus, the structure of philosopher I is given here. Do while loop, infinite do while loop. Obtain the two chopsticks to immediate right and left. So first call wait function. Wait function means has to grab the chopstick waiting for the resource, waiting for one chopstick and another chopstick either to left side or right side. Then eat. After calling these two functions, philosopher can grab the chopstick and she can able to eat. Then after eating, she will release both the chopsticks by calling signal. Signal function, one chopstick, immediate right and left. After that, after releasing the chopstick, she will go to a state called as thinking. Okay, understood the code, right? First call wait function to grab the chopstick, then eat with the help of two chopstick, then release both the chopstick by calling signal function. Although this solution guarantees that no two neighbors are eating simultaneously, it nevertheless must be rejected because it could create a deadlock. Suppose that all five philosophers become hungry at the same time and each grabs her left chopstick. Consider that situation. All five are hungry and they grab their left chopstick. All the elements of the chopstick will now be equal to 0. No chopsticks are available. One chopstick is in the hand of a philosopher. When each philosopher tries to grab her right chopstick, she will be delayed forever. Understood the situation? All five philosophers are hungry. They will grab their left chopstick like this. Each and every philosopher is having one chopstick which is present on the left hand side, but to eat they require two chopsticks. The two chopsticks are not at all available for them. Several possible solutions to the deadlock problem are given over here. There are five solutions. First one, allow at most four philosophers to be sitting simultaneously at the table. Do not allow five, allow only four. Allow a philosopher to pick up her chopsticks only if both chopsticks are available. If both are available, then only pick. Then another solution, use an asymmetric solution. That is, allow an odd philosopher to pick up first left and then right, and even philosopher picks up right chopstick and then left chopstick. And last solution is using monitors. Very important one. Let us consider how to solve dining philosopher problem using monitors. Although semaphores provide a convenient and effective mechanism for process synchronization, using them incorrectly can result in timing errors that are difficult to detect. Since these errors happen only if particular execution sequences take place and these sequences do not always occur. We have seen an example of errors in the use of counters in our solution to the producer-consumer problem. In that example, the timing problem happened only rarely and even the counter value appeared to be reasonable off by only one. Nevertheless, the solution is obviously not an acceptable one. It is for this reason that semaphores were introduced in the first place. This is the schematic view of a monitor. Consider this one as this circle which is having initialization code. Each and every monitor is having some initialization code, then which is followed by some operations, important operations, and they are going to use shared data. So this shared data can make use of pointers like this, singly linked list like this, which is called as entry queue. So monitor is a module that encapsulates shared data structure, procedures that operate on shared data, and synchronization between concurrent procedure and invocation. This is the view of a monitor, which is followed by syntax. How to make use of this monitor concept to implement dining philosopher problem. You can see our keyword monitor followed by monitor name, then declarations. We can define any number of procedures. Procedure P1 with the prototype and function. procedure P2, P3, P4, like that, procedure P1 with the prototype and function. Then initialization code, then end of monitor. Now, a monitor based solution to dining philosophers problem. We will illustrate monitor concept by representing a deadlock-free solution to the dining philosopher's problem. This solution imposes the restriction that a philosopher may pick up her chopsticks only if both of them are available. To code this solution, we need to distinguish among three states in which we may find a philosopher. For this purpose, we introduce the following data structure, that is enumeration, thinking, hungry and eating. Three states: thinking, hungry and eating. First key insight is pick up two chopsticks only if both are free. So this avoids deadlock. Another insight is that a philosopher moves to his or her eating state only if both neighbors are not in their eating states. Okay, if both left and right philosophers are not in the eating state, then only he can pick. Thus, need to define a state for each philosopher. Second insight, if one of my neighbors is eating and I am hungry, ask them to signal me when they are done. I am hungry and my neighbor is eating. I can inform her that once it is over, just intimate me. States of each philosophers are thinking, hungry and eating. Thus need condition variable to signal waiting, hungry philosophers. Also, we need two functions, pick up and put down. Pick up means picking up the chopstick. Put down means putting the chopsticks down after eating. The code pick up and put down is executed in the following sequence. First call pick up to grab the chopstick, then eat, then call put down, so that the chopstick can be used by another philosopher. This is the code, very important one. If you understand this code, then you can easily write the code. See, first line, monitor DP. Name of the monitor is DP. We have the status as 5 states. Condition self of 5. Condition variable array, which is self having 5 memory locations. First pickup function int I. State of I is equal to hungry. Clear, explanation is over here. Indicate that I am hungry. State of I is set to hungry means the particular philosopher is hungry. Then he has to test whether the chopsticks are available or not. Set state to eating in test only if my left and right philosophers are not eating. First make sure that my left and right philosophers are not eating. Then if state of I is not equal to eating, then self of I dot wait. If I am unable to eat, wait to be signaled. If I am not able to get the chopstick, I am in the waiting state. So this is about the pickup. Okay, understand? No, pickup means try to pick up the chopstick. If possible, pick up. If not, just sit in the waiting state. Then what about put down function? Put down function is used to put down the chopstick. State of I is equal to thinking. Okay. Test, call the test function with I plus 1 mod 5 because we are having 5 philosophers. Test of I minus 1 mod 5. I plus 1 and I minus 1 to indicate left and right chopstick. Okay. So if that is the case, if eating is over for one philosopher, then he or she can put on the chopstick. Test function. Test whether the philosopher is eating or not eating. If state of I plus 1 mod 5 is not equal to eating, I minus 1 is also not equal to eating. Are you following? I plus 1, left philosopher is not eating, right philosopher is also not eating, and I am hungry, particular philosopher is hungry, then state of I is equal to eating. It is possible because left is not eating, right is also not eating, means both chopsticks are free and I am hungry. I can eat with the help of these two chopsticks. After eating, signal. Signal has no effect during pickup but is important to wake up waiting hungry philosophers during put down. This is initialization code as in this picture. Yes, initialization code. Okay, initialization code means which will work in the variables which are initialized in the beginning. For I is equal to 0 to 4, state of initially state is set as thinking only. Thinking state can be changed to waiting or eating, hungry or eating state. So this is the solution using monitor. Solution to the dining philosopher problem using monitor. So this is the end of chapter 6 of module 2. Happy learning students. Thank you. Thank you one and all.